classify the matter into three categories such as solids, liquids, and gases. But whether a substance will exist as a solid or a liquid or a gas, it always depends on the net effect of the two main opposing factors. They are the interparticle attractive forces and thermal energy. Let's have a look at the first one, interparticle attractive forces. The interparticle attractive forces are the forces of attraction existing between atoms, molecules, or ions which tend to keep them closer to one another so as to have a fixed shape. Thermal energy. Thermal energy is the energy possessed by the constituent particles due to temperature. With the increase in temperature, the molecules gain the energy and the randomization of the motion increases. That implies thermal energy is directly proportional to temperature. If we increase the temperature, the thermal energy of the constituent particles increases, and you can see the randomness in the motions is also increasing. When the interparticle attractive forces are very less as compared to the thermal energy, the molecules have a randomization in motion and we say that it exists in gaseous state. When the interparticle attractive forces are slightly more than the thermal energy, we say that the substance exists in a liquid state. And if the interparticle attractive forces are very much greater than the thermal energy, that is, at a low temperature when thermal energy is low, the interparticle attractive forces increases, the randomization in motion decreases, and the particles occupy a fixed shape, that is, they now exist as solid state, which have a fixed motion, they have a rigidity, and they are incompressible. Let us see the classification of solids. When we look at diamond and glass, their structure looks solid. But when we look at the microscopic level, we see that there is a difference in the arrangement of the molecules in glasses and solids. The particles are arranged in an orderly fashion in diamonds, whereas if we talk about the glasses, the particles are completely disorganized. This arrangement of particles in orderly and disorganized manner leads to the classification of solids as crystalline and amorphous solids. Let us see about the crystalline solids. When we talk about crystalline solids, the constituent particles such as atoms or ions or molecules are regularly arranged in a definite pattern for a long range. Here, the arrangement of particles is so fixed and regular that if we see the arrangement of particles on any one side, we can very easily predict the pattern of the particles on the other side of the molecule. This is a regular pattern of arrangement which repeats itself after a periodic over the entire crystal. Example: sodium chloride, table salt; diamond, solid iodine; gold, quartz. Now let us see the amorphous solids. When we talk about the amorphous solids, the arrangement of particles is not in an orderly fashion. You can very clearly see that there are regularly arranged particles, but they are present between the non-orderly, that is non-properly arranged structures, and hence they do not have a fixed shape, or we can say that they do not have a regular geometry. We can also say that the overall arrangement of the particles is distorted. For example, glass, rubber, and plastics. Now let's study the difference between the crystalline and amorphous solids. When we talk about the crystalline solids, we have already seen that they have a regular geometry, that is, the molecules are arranged in a very regular pattern at every portion. Due to this, the solids melt at a very high temperature. but the temperatures remain the same for the whole of the solid. But when we talk about the amorphous, every portion of the amorphous has different geometry, and due to this they have different melting temperature. That is, they melt over a wide range of temperature that is not fixed like 100 degree or 150 degrees Celsius. Now, if we talk about the crystalline structures, they are anisotropic in nature. That is, the physical properties are not same in all the directions. Suppose we see a range of A and B, we can see that all the particles are blue. Suppose if we take D and C, we can see there is an alternate arrangement of red and blue. And if we take the next axis E, we can see that there is also an alternate arrangement, but the distance between them has widely increased. So, we can say that due to the difference in arrangement of particles in all the different directions, their physical properties like electrical resistance, refractive index, thermal expansion are varied in directions. That is, they have values when we measure in different directions would be different. While we talk about the amorphous solids, they are isotropic in nature. That is, the physical properties are same in all the directions. That is, if we take the axis, the arrangements is completely irregular, and hence the physical properties like electrical resistance, refractive index and thermal expansion would have negligible variation in the different directions we study. Now, when we see the crystalline solid and we cut its edge with a sharp knife, we can see that there is a clean cleavage and a smooth surface has occurred. Whereas in amorphous solids, we get the irregular surfaces, that is, we get the rough edges. Next difference, that is, now if we talk about the classification of the solids. The crystalline solids can be classified into 4 different categories depending upon the constituent particles and the nature of attractive forces which operate between these constituent particles. They are molecular solids, ionic solids, covalent or network solids, and last is the metallic solids. Now, let's have the first look at the molecular solids. When we talk about the molecular solids, the constituent particles, as the name suggests, are molecules. And depending upon the nature of the molecules, these can further be classified into 3 different types. That is, non-polar molecular solids, polar molecular solids, and the last one is hydrogen bonded molecular solids. Now let's study about the metallic solids, where the constituent particles are metal ions and free electrons. When we talk about metals, we know that they have a tendency to lose electron and become positively charged ions. These positively charged metal ions are called as kernels, and the free electrons which are present in this particular metal ions are free to move and can flow through in anywhere. These electrons have the tendency to get attracted towards the positively charged metal ions, and hence they keep them on place because of the attractive forces present between those kernels, that is positively charged metal ions, and the negatively charged electrons. Because of this forces, the metals have strong metallic bonds, that is, they would have high melting and boiling points. These free electrons are also responsible for the high electrical and thermal conductivity. And because of these also, the metals have the tendency to possess colors. For example, copper, iron, aluminium, and silver, zinc. Now, let us study about the ionic solids. When we talk about the ionic solids, their constituent particles are cations and anions, which are regularly arranged in a 3-dimensional manner. These cations and anions are held together by electrostatic forces of attraction, and hence they are not free to move and are closely packed. The structure is hard and brittle, and due to this, the solids possess high melting and boiling points. Now, if we talk about the next thing in the ionic solids, that is, they are soluble in polar solvents like water, but they are insoluble in non-polar solvents like benzene. Ionic solids are insulator when they are in solid state, but they are very good conductors in aqueous or molten states. Now the question arises that why are these ionic solids good conductors in the molten state but not a good conductor when in the solid state? In the ionic solids, the electrical conductivity is basically due to the movement of ions. When they are in a solid state, they are in a fixed position and are not free to move in any which directions. Whereas, if we talk about the molten state or the aqueous solutions, the individual ions are free to move about in the whole container. And when potential difference is applied across them, they act as a charged particle and hence are good conductors of heat and electricity. The examples are sodium chloride, zinc sulfide, magnesium oxide, cesium chloride, etc. The next is the covalent solids, which are also known as the network solids. In the covalent solids, the constituent particles are non-metals which are linked to the other atom by a covalent bond, which gives rise to a network structure, that is, one atom linked to the other atom with the help of covalent bonds, which is forming a structure or a network of solids. These are very strong because of the presence of the covalent bonds. When we talk about them, as they have a fixed shape, they are hard and brittle and they have extremely high melting and boiling points. And they may also decompose before the melting is achieved. These covalent solids are bad conductors of electricity due to the absence of free ions. One of the most common example is diamond, where the molecules or the constituent particles are arranged in a network with the help of covalent bonds. There is a three-dimensional structure in diamond, but there is an exception in covalent solids which is a good conductor, and that is none other than graphite. Though it is a covalent solid, unlike the other covalent solid, it is a very good conductor of electricity and is also soft, unlike the other covalent solids which are hard. This is due to the typical two-dimensional layered structure which the graphite possesses. Here, the graphite has a arrangement where the molecules are arranged above one another in the form of layers and have a tetravalent nature, that is, the combining capacity with four other atoms. When we talk about the tetrahedral structure, we can see that when the molecules are arranged in a regular atom, the fourth valence electron is free and is not in a bonded state, and hence this free valence electron is free to move amongst the layers which are present between the carbon atoms. Due to the movement of these particular electrons, the electrical conductivity can be generated because they are charge carriers, and hence we can say that graphite is a good conductor. The force of attraction between each layer of graphite is very weak and hence it can slide very easily over one another. This leads to the soft nature and hence it can be used as a solid lubricant. That is, it can have a slide one over the other. If we talk about the examples, they are diamond, silicon carbide, Now let us study about the crystal lattice and the unit cells. We know that the main characteristic of crystalline solid is the regular and repeating pattern of the constituent particles, be it atoms, molecules, or ions. That is, they would be repeating each other in a structure, and these can be replaced or these can be represented with points in a crystal. There is a regular three-dimensional arrangement of the constituent particles in a particular solid, as we have already seen the four types of solids. These regular arrangement of molecules, that is the constituent particles, at a fixed point is known as the crystal lattices. That is, there would be a fixed place where these constituent particles would be placed. According to these regular arrangement, the French mathematician Bevis Lattice suggested the 14 particular three-dimensional lattice structures, and to honor him we call them as the Bevis lattices. Now let us study about these particular Bevis lattices and the crystals and the unit cells. When we talk about the solids, we have already seen that whatever kind of solid it is, there are lattice points, that is, there are fixed places where these constituent particles are placed. When we look at the structure, we can see that there is a regular arrangement of lattice point which is repeating itself in the entire structure of the molecule. This particular regular arrangement is known as a unit cell. That is, this unit cell is considered as the smallest unit of a particular structure or crystal lattice. That is, with the repeating unit cells, we would get an entire structured molecule. Now, a particular unit cell is represented by its three edges A, B, and C directed along X, Y, and Z axis. Please note that these A, B, and C, that is, these edges, may or may not be perpendicular to each other. That is, in some cases they may be perpendicular to each other, and in some cases they may be inclined to each other. If you look at this particular cell, the angle between B and C edge is alpha, that between A and C is beta, and the angle between A and B is denoted by gamma. Now, we can say that there are 6 basic parameters of a particular unit cell. That is, the 3 edges and the 3 particular angles. These edge lengths and the face angles have a perfect combination, and resulting in the combination of these edges and the angles between them, there are 7 possible constituents. That is, there are 7 crystal systems based upon them. They are the cubical unit cell, the trigonal unit cell, the orthorhombic unit cell, the rhombic unit cell, the monoclinic unit cell. Next is the hexagonal unit cell, the triclinic unit cell. So now let us arrange all these crystal systems in a form of a table. I request you all to please memorize this table, as it is very important from the competitive as well as CBSE exam point of view. Now let us study about the types of unit cells. Based on the position of the constituent particles in a unit cell, the unit cells are broadly classified into number 1, the primitive unit cells, and number 2, the centered unit cells. The primitive unit cells are basically the cells when the constituent particles are present only at the corners of the unit cell. It is denoted by the letter P. Here, no molecule is present anywhere except the corners. Next, if we talk about the centered unit cell, the constituent particles will not only be present at the corner positions, but they will also be present in some other position apart from the corner position. That is, they may be located anywhere else along with the corners. They are further classified into body-centered unit cell, face-centered unit cell, and end-centered unit cells. Now, let's have the very first look at the body-centered unit cell. As you can see in the diagram there, it is the type of unit cell where the constituent particles are present in the center of the unit cell apart from the particles present at the corner positions. As one particle is present in the center of the body of the cell, it is called as the body-centered unit cell. Next is the face-centered cubic unit cell. As the name itself suggests that apart from the particles present at the corners of the primitive unit cell, the other constituent particles would be present one each at the faces of the cubic unit cell.